Okay, well, it's a pleasure to be back here. This is actually the second time I'm speaking at this conference. Those guys clearly didn't learn anything from the last time, but I'm happy to be back in beautiful Bratislava. And yeah, we're coming to the Beyond part. We're almost there. 3 more speakers, and then we have the after party. A little bit about myself. I'm going to be today speaking about one of my activities, the logo you see there on the top and the middle, which is Prometheus Labs Technologies, which is a space biotech company. Yes, it's not made up. There's such a thing as a space biotech sector, very small sector so far. I'll talk about this. But just so you know, and some of you may already know me, this is not the only thing I'm doing in the space sector. Actually, arguably my main job is I'm an early stage space venture capital investor. So I invest in young space startups like the ones that pitched this morning at the seed and pre-seed stage. This is through my venture fund, E2MC, which stands for Earth to Mars Capital. And I'm also quite active in space outreach. So I lecture at some universities like the Swiss Institute of Technology in Lausanne. I'm a mentor at some space incubators. I have a podcast, which I'll show you later on, and I wrote an introductory book to the space economy. But enough about me. Let's see. I did want to show you a video. Let's see whether this is going to... Do we have the video?
No active ingredients for drugs are tested in animal experiments. Because animals and humans are different, many compounds fail late in the expensive development process. Toxicity tests on miniature organs could eliminate the need for animal experiments and speed up the development of new drugs.
On Earth, cells normally grow flat in 2D in simple cell cultures. 3D structures always need a support structure on Earth because of gravity, such as a skeleton in our bodies. In space, however, there's no need for support structures. We produce small, organ-like pieces of tissue from stem cells from bone marrow.
Thank you. That was it? No, I'm kidding. So if you can go back to the presentation, please. And also, yeah, thank you. For the guys back there, if there was supposed to be a 20-minute timer, it's actually not running, but I can also keep time on my watch, it's fine. So, okay, so the video already gave you some idea. So Prometheus is a space biotech company. We produce certain biological things in space. And so, of course, you know, the first question any reasonable person would ask is like, why the hell would you go and produce something in space? I mean, that sounds way too complicated and expensive, right? Unless maybe the example from one of the gentlemen speakers earlier this year, earlier today, who I think wanted to do drugs in space, and I can see the sort of legal argument maybe, but no, the reason we do things in microgravity, and some of the speakers earlier today may have already explained this a little bit, is the microgravity conditions have certain interesting follow-on effects. Like, for example, there's no sedimentation, no buoyancy. That means you can mix or bind stuff that you can't mix or bind under 1G conditions on Earth. For what we're doing, which is something called organoids, which I'll explain, it's another thing that's interesting, which means if there's no gravity vector pulling you, well, basically down, you can grow things very cleanly in 3 dimensions, because they just naturally expand every which way, right? And so what we are growing in space is what you see here. I mean, it's very small in the middle. These are called organoids, human tissue organoids. And these are basically 3-dimensional clumps of human organ tissue. And we do this in space because they grow, again, very cleanly in 3 dimensions automatically. We cannot do this on Earth. So if you try to do it on Earth, they basically collapse into a 2-dimensional blob. And the only way you can avoid the collapse to a two-dimensional blob on Earth is if you put a support structure in there, what we call a matrix or a scaffold. But it introduces foreign materials, and those foreign materials have a number of undesired effects. We also found that these organoids we produce in space are better in other ways than organoids we can produce on Earth. So, for example, what we call the differentiation into the final tissue, whether that's a liver tissue or a fat tissue or whatever, is better than what we achieve on Earth. We actually don't know why, it's just the way it is. And very importantly, from a commercial point of view, we find that if we produce a batch of these on space, let's say you produce 100 organoids, you want all of them ideally to look exactly like them, well, not exactly, but you want them to be as similar as possible, because you use them, I'll talk about this, for example, in biological testing, and in testing you want to be able to reproduce results. So you want all of them to have a very uniform batch quality. And this is very hard to achieve on Earth and much easier in space, again, for reasons we don't only understand. But a number of reasons to do these human tissue organoids in space. And just to walk you a little bit through the process, what we're actually doing. So we start with stem cells, so-called mesenchymal stem cells from adult donors. If you remember your high school biology, stem cells, specifically here we'll be using what's called pluripotent stem cells. They can differentiate into a number of final organ tissues. I will show you this. We have produced 5 different types of organ tissues in space already: a liver, cartilage, bone, adipose, which is fat, and neural tissue. We could produce others, for example, like cardiac as well. So we start with these stem cells, which you can just buy. Like there's adult donors for these, and there's companies you can buy the stem cells from. Then we kind of go through our proprietary process and basically start seeding them and let them proliferate. So we start a mini organoid on Earth. Then we fly to space, and we fly to space for about 4 weeks. We could probably do it in 2 weeks. Why do we fly for 4 weeks? Well, because we have to get a ride up and down, and we're substantially dependent on what's called the commercial resupply mission schedule on the International Space Station. So we do this on the International Space Station. And then after 4 weeks, we get a ride back, we come back down on the SpaceX capsule, and we come back to Earth. So this is the process. And another question we always get, and it's a very important question, is, well, can't you just do this on Earth somehow? Can you simulate microgravity on Earth? And it's like, well, no, at least not in the way we need it. What we need is sustained microgravity, as I said, for at least 2 weeks. There is short-term microgravity you can achieve outside of space. For example, we have what's called fall towers on Earth, right? So very big towers, for example, at the University of Bremen, it's like over 100 meters high, and you literally drop something from the top. And while it is dropping, and it's also in a vacuum, while it's dropping, it is experiencing microgravity. The problem is the drop is 4 seconds long, so that doesn't really help us for our process requiring 2 weeks. There's also parabolic flights, where aircraft flies parabolas. A typical parabola is about 20 seconds. Useful for some stuff, definitely not useful for us. Suborbital rocket flights, like Virgin Galactic, get a few minutes, also not useful for us. We have to go to space. Some of you actually really know that kind of stuff and equipment on Earth. Yes, there are things called clinostat and random positioning machines where you just keep spinning stuff and basically trying to cancel out the gravity vector. We cannot use that. It introduces a number of other undesired effects, for example, shearing effects on the cells, and it doesn't work. The gene expression is completely different. So we have to go to space. As I mentioned, this is not conceptual. Like, the company is a spin-off from the University of Zurich. There was a project sponsored by the university and also sponsored by these guys, by Airbus, to grow these organoids. And as part of these projects, 2 missions were flown to the ISS. Total of 472 of these organoids were produced. We found, again, really high batch quality. Every organoid, we got them in little vials. Every vial resulted in an organoids. We had male donors, female donors, different age groups. We were able to keep them viable for a couple of months afterwards. You see on the right, actually, maybe it's a little bit small, but you see the comparison of a 2-dimensional tissue on top, our space organoids in the middle, and then a textbook reference for liver tissue on the bottom. You can tell ours is much closer to the textbook reference. So why is all of this important? Like, what do you do with like little cell balls? Well, you saw this in the video already. We were talking about drug development being really expensive, right? And why is drug development really expensive? Like estimated $1.4 billion on average for a new drug. And by the way, there's newer studies that peg this actually much, much higher. It might be as high as $4 or $5 billion. Well, that's because for every successful drug you develop, you actually have to pay for all of the failures as well. And many drugs fail during what we call clinical trials. Clinical trials, as you may know, is when you actually test it on human beings, right? And when you test it on human beings, well, you test it for what we call toxicity, right? Is it toxic to your body? And then, of course, also for what we call efficacy. Does it actually do what we wanted to do as a drug, right? And so many of them fail later stage. And that's very bad because testing something on humans is very expensive typically, because there's for right reasons, there's very extensive safety protocols, as you can imagine, right? So, a clinical trial, and there's 3 phases of these. Each phase can cost you sometimes tens of millions of dollars. Sometimes it's complex, it can cost you hundreds of millions of dollars, right? So if you have a new drug under development and then you spend a few $100 million and then it fails, that's not good. This is why this number is so high, right? So if you could eliminate that failure rate, that would be really, really important. And the way you would like to eliminate this is before you start giving it to humans and incurring these really expensive trials, right? It's what we call the preclinical testing, right? And so how do we do the preclinical testing at the moment? Well, substantially on animals, right? Things like rodents, but also some other animals, like sometimes worms, zebrafish, all the way up to what we call non-human primates, right? Basically monkeys. But that has 2 other issues. The animals are not humans, right? I mean, that should be fairly obvious. Of course, non-human primate, you're getting relatively close to human, but you're not a human. And of course, a rodent is arguably completely different. That's one problem. The second problem is what you see here on the far right is the 100 million, just in the US, we estimate that over 100 million animals are killed every year between the pharma and cosmetics industry. I mean, that's just quite a sad number. And so this is the ethical problem here. And then the third problem, which is not even on here, is that the animals, it's actually not easy to keep the animals. They're actually more expensive than, because again, there's a number of ethical protocols with the animals, especially if it's more developed animals like the non-human primates, the monkeys. So these are more expensive than people generally think. Like a non-human primate model, like one monkey can be like a few $100,000, right? And then the last anecdote I tell you, which I kind of find entertaining, a couple of years ago I was going to a biotech conference in San Francisco. We're talking about all of these models, right? I was talking about monkeys and being expensive. And then somebody from the pharma industry is like, yeah, not only are they expensive, but now because of COVID, we actually have a monkey shortage. I was like, that's something I never expected to hear in my life, the term monkey shortage. There you go. So this is using organoids to substitute animal models in biological testing, including preclinical drug testing, okay? The second use case is regenerative medicine. In regenerative medicine, the ultimate dream many of us have, people like me in this field, is that you will ultimately be able to have a full, personalized replacement organ. So, I'm here, I'm spending too much time with Iggy and Adam in Bratislava. Clearly, very soon I'll need a replacement liver. I mean, it's just a given, right? And so, the way this works right now, as you may know, is that we need a donor, right? They try to match somebody as closely to your physiology, they try to match somebody as closely as possible to your body, simplistically speaking, as possible, so the organ, somebody's donor liver doesn't get rejected. Rejection is bad, right? Like the extreme, you die, really bad. The dream we have is that we would take our process, we would start with, I need a new liver because of Adam and Iggy. We start with my stem cells. We produce organ tissue, organoids, for my stem cells, which then differentiates into liver organoids. We use those liver organoids as the quote-unquote ink for a 3D bioprinter, which basically constructs a replacement liver. It constructs like exactly the way it should be, like the shape it should be, like vascularization, right? Because obviously you need blood vessels in the organ as well, layering the different cell types in the right way, and so forth. Now, this is not something that's around the corner. That's probably a few years away. But this will happen. There's no known at least not known to me, technological obstacle why this wouldn't happen. We just have to refine our methods, we have to keep developing it, and we have to sort of first do a small one, bigger one, bigger one, bigger one, but this will happen. And then if we have such a replacement organ that's really my personalized organ, there will never be any, there's no reason to believe there would ever be any rejection issue, because those are my cells. This is genetically me. There shouldn't be any sort of rejection, immune system issues. And again, this is a big issue right now. Like even when transplantation of donor organs work these days, very often those recipients have to be on immunosuppressant drugs for the rest of their lives. And sometimes drugs that can cost tens of thousands of dollars per month. And even so, in the US, this number changes all the time, but typically a little bit over 100,000 people are on the waiting list for donor organs in the US. And then because there are not enough donor organs around, this number also changes slightly, but about 17 per day die waiting for an organ, which of course is not ideal. Both of these markets, the biological testing market as well as what we call the regenerative medicine market, they're already sort of in the hundreds of millions of dollar markets, and they're both expected to grow at a clip of like, probably about 20% per annum for the foreseeable future into billion-dollar markets. So also commercially quite interesting. Why is now the right time to do this? We actually have known about this sort of scientifically, that this makes sense. But first, speaking about this substitution of animal tests that I already talked about a lot, right? That ethically we want to substitute animal tests. For a change, politicians are smart enough to agree with this. Like actually the US Congress and then President Biden approved what's called the FDA Modernization Act, a new law in the US at the very end of 2022, specifically allowing the substitution of animal tests in drug testing with models like our model. The other reason it's the right time to do this now is because, of course, we want to do this at scale. And right now we have to go to the ISS, right? Because that's the only way where we can produce things like this. But the ISS, and some people earlier on the panel were talking about this, the ISS was never designed as a commercial production facility. It was designed as a relatively small-scale government academic laboratory. So we need production platforms like SpaceForge, who are here, and actually they're an investment in my venture fund. But there's a number of companies like SpaceForge on the horizon. Some of them are space stations, some of them are free flyers like SpaceForge. There's now enough of these projects, some of them with very substantial funding, that I'm comfortable at Prometheus that there is going to be platforms around where I can produce my things at scale. And also, as a result of what all of these guys are doing, the price of producing, the price of taking something to space and bringing it back is also expected to drop quite dramatically. We can skip over this. This is basically just saying that we won a bunch of grants already. What we're doing is a very specialized field, space biotech. There is very, very few people who have both biotech expertise and space expertise. We have both. I'm hopefully somewhat of a space expert. I'm not the only one at the company. But the rest of the team substantially all are life sciences PhDs. I'm actually the only guy who doesn't have a life sciences PhD, I think, which of course I'm very bitter about. Right, so right now we are conducting further R&D projects. We are expecting to go back to space either later this year or the beginning of 2025 and start growing these organoids now for commercial beta testing customers. That all goes well, we start scaling up from there. And then of course the idea is to bring in some of these newer platforms like SpaceForge that I talked about. So that's what I wanted to tell you about Prometheus and what space biotech is as an example of space biotech. So we close up some of these other activities about myself in case you are interested in learning more, you still want to learn more about the space sector. I know some of the audience here are just getting into the space sector, looking for other places to learn about the space sector. I mentioned I have a podcast. It's almost every week. The QR code takes to a podcast, Space Business Podcast, where I typically interview space entrepreneurs, but sometimes also other cool people from the space sector, like astronauts and people like that. I also wrote an introductory book to the space economy, which describes what the space economy is, what type of business models there are, what the trends are, what the future next 10 years would look like. Again, the QR code will take you to this book. It's called To Infinity. And I think this is my LinkedIn. I'm sometimes on X, not as much as other people. But yeah, this is where you can find me. I hope you found this interesting as an introduction to space biotech and a specific application. And I know there's going to be Q&A after the next 2 talks, you'll have a chance to ask questions about all of this as well. Thank you very much.